Energy can be called a capacity to do work. There are different kinds of energy. For instance, energy of movement, electrical energy, chemical energy, in a match head, for instance, and heat, which is also a form of energy. We keep up our strength with food, which gives our bodies heat energy. Energy can usually be changed from one form into another. Energy of movement can be changed into electrical energy, and electrical energy back to energy of movement. Electrical energy into heat, and energy of movement into heat. But although energy can change in kind, it can never change in quantity. The amount of electrical energy being used up here is equal to the amount of movement energy produced, or to the amount of heat energy produced. This motor changes electrical energy into movement energy. It drives a lathe, and the energy does useful work, cutting the metal. While the work is being done, the energy doesn't disappear. It changes into heat. Heat engines are machines for changing heat energy into energy of movement. Their success depends on how well they can do it. Men have always struggled to improve their living conditions. This has meant dragging heavy loads and raising heavy weights. To their own strength, men gradually learned to add other kinds of power. In their time, these were sufficient. But as populations grew, trade and commerce widened. Men were compelled to seek a new kind of power. 2,000 years ago, a Greek named Hero devised a machine which looked rather like this. His machine showed for the first time that heat could produce continuous movement. But for practical purposes, it was useless. 1,600 years later, men had to turn again to heat as a source of power. By the 17th century, they were experimenting with machines, heat engines, to obtain from heat a continuous supply of work. They did this by means of steam. These early machines were crude and simple, but they worked. And by the beginning of the 18th century, Newcomen's engines were giving men greater and more reliable power than they had ever known before. By the end of the 18th century, steam engines had been much improved. During the 19th century, they were being used for all kinds of purposes. They became more complicated as improvements were made. But the steam engine was large and often clumsy. So another kind of heat engine was investigated, the internal combustion engine. Otto's first gas engine of 1864 led to the gasoline engine, and to the diesel engine. All these machines, old and new, have a common purpose: to turn heat into work. When something is heated, it exerts a push because it tries to expand. Steam pushes up the lid of a kettle. It is in this kind of way that all heat engines change heat into work. They depend on fundamental laws concerned with heat and temperature. Temperature measures whether something is hotter or colder than something else. We judge it roughly by sense of touch and measure it accurately with a thermometer. Temperature is not the same thing as heat. These two burners both give out heat at the same rate. Put a very little milk into one pan and a much greater amount in the other. After a few moments, the milk in the left-hand pan has come to the boil. The other milk is still quite cool. Both pans have received an equal amount of heat energy, but this heat, squeezed into a little milk, produces a much higher temperature than the same amount of heat spread out through much more milk. Temperature then measures the concentration of heat energy. How do heat and temperature concern heat engines? In a locomotive, the steam gets its heat from the furnace at a high temperature. The steam changes a part of this heat into work, and it then gives up the remaining heat, now at a much lower temperature, to the surrounding atmosphere. As energy can only change in kind, not in quantity, the heat energy supplied by the furnace is equal to the work done plus the heat given up to the atmosphere. The same things happen in steam turbines, such as in power stations. Heat at a high temperature from the furnace enters the steam, which then goes into the turbine. Inside the turbine are rotating rings of blades. The steam expands through nozzles in a continuous stream and rushes onto the blades, pushing them round to provide energy of movement. The steam then gives up its remaining heat at a much lower temperature to cooling water and eventually to the atmosphere outside. And the same in a car engine. The source of heat is the burning of fuel in the cylinder. Here it is in slow motion. This heat, at a high temperature, enters the gases in the cylinder. The gases turn part of it into work. They then give up the remaining heat at a much lower temperature by way of the exhaust to the atmosphere. So all heat engines need the same three things: a source of heat at a high temperature, an agency, such as steam, which can take in this heat and change a part of it into movement or work, or it may be other gases, as in the car engine. Finally, something colder than the source of heat, to which the agency must give up the remaining heat at a lower temperature. This is, in fact, the engine's surroundings. All heat engines have the same purpose: to obtain useful work from heat. The heat comes from burning fuel, but fuel costs money. So it's important for any heat engine to get as much work as possible from the fuel, that is, from the heat. The percentage of useful work obtained from a quantity of heat is called thermal efficiency. Hero's device of 2,000 years ago had a thermal efficiency of practically nothing. it could just about turn itself round and no more. Even the first practical steam engines had low thermal efficiencies. The Newcomen engines of the 18th century were much less than 1% efficient. James Watt's engines raised the figure to about 1%, while the later Cornish pumping engines may have reached 2%. Modern engines, on the whole, do a bit better. An express steam locomotive can reach about 8%. Larger, more elaborate steam engines reach about 17%. A motor car engine is higher, 22%. A modern steam turbine gives 28%. A diesel engine gives 35%. So even the most efficient engines today can only turn about 1/3 of the heat they consume into useful work. The reason is fundamental. It has to do with the behavior of heat itself. In doing its work, the movement energy provided by the lathe motor becomes heat energy. This change, movement into heat, is much more common than all other kinds of energy change. It happens all the time, not only in engineering, but in everyday life. Sometimes the heat produced is obvious, sometimes not. But whenever anything moves, when feet tread on pavements, when snooker balls collide, movement changes inevitably into heat. Always this way, never this. If it did, heat could come out of the air of its own accord, change into movement and drive the cart backwards, pulling the horse after it. Heat engines put the cart before the horse because they try to do this very difficult thing, to turn heat energy into energy of movement, the opposite direction to the natural change. And the efficiency with which they do it is low. They can't even do it at all unless there are two different temperatures, a hot and a cold. This is because of another property of heat. It always flows from hot to cold. Put something hot in contact with something cold, and heat flows naturally out of the hot thing into the cold one. In the same way, the heat from a furnace, if we let it, would all pass straight into the cooler room and eventually out to the atmosphere. A heat engine depends for its very working on this flow of heat from hot to cold. We make the heat flow through the engine, which can intercept a part of the heat and change it into useful work. But the rest of the heat must continue on its downward flow. The engine must give it up at a lower temperature to its surroundings. The heat given up is always a high percentage of the heat taken in. This, then, is why heat engines have such low thermal efficiencies. How can they be increased? Heat engines depend on the flow of heat from hot to cold. So the longer this flow, the more chance there is to change heat into work. So the bigger the temperature difference in the engine, the better. For instance, here is a compound steam engine. The steam comes from the boiler at 160 degrees centigrade into the cylinder. Here it expands, pushing the piston to supply useful work, and cooling from 160 degrees down to 110 degrees. If the engine ended here, the steam would now give up its remaining heat to the surrounding air. But this is much cooler, and this temperature difference can provide some extra work. So the steam is actually led from the cylinder into a second one. Here it expands further and supplies this extra work and cools further down to 85 degrees. Finally, it is led away and gives up its remaining heat through cooling water to the surroundings. So a bigger temperature drop in the steam has been used, and more work is produced from the same original quantity of heat, which means higher thermal efficiency. And this is a general rule for all heat engines. The bigger the temperature drop in the working agency as it goes through the engine, the higher the thermal efficiency. So thermal efficiency can be increased by taking in the heat at a higher temperature and by giving up the heat at a lower temperature. First, let's deal with the low temperature end. Adding on a second cylinder allows the steam to be used down to 85 degrees. The thermal efficiency of this particular compound engine is about 10%. This engine goes one better. It has 3 cylinders. The steam goes through each in turn, and the total temperature drop is bigger than in the 2-cylinder compound. The steam can be used down to 60 degrees, and this increases the efficiency to 15%. The steam turbine goes many times better. Each ring of blades is like a separate cylinder. The steam expands onto each in turn, cooling as it goes. Some turbines have a second complete set of rings, and this allows the steam to expand and cool still more. Work is got from the steam right down to 45 degrees. Efficiency is much higher, 28%. So, thermal efficiency is increased by using steam down to lower and lower temperatures. The same applies in other engines. For instance, diesel engines have an efficiency of about 35%, much higher than gasoline engines. This is chiefly due to the diesel's high compression. The gases in the cylinders are compressed relatively more in a diesel than in a gasoline engine. So the hot gases expand more in the diesel and do work down to a lower temperature. The exhaust gases leave the diesel engine at about 400 degrees centigrade. In the gasoline engine, they are never less than 750 degrees. Put a drop of oil onto a diesel exhaust pipe, nothing much happens. But a gasoline engine's exhaust is much hotter, and the same oil burns. So much for increasing thermal efficiency by pushing the low temperature down. But it can also be increased by pushing the high temperature up. The steam turbine is much more efficient than the compound steam engine because the steam leaves at a much lower temperature and also enters at a much higher temperature. 500 degrees centigrade as against 160 degrees. Internal combustion engines are more efficient than steam engines because their upper temperature is far higher than in steam engines, over 2,000 degrees centigrade. At such a high temperature, the whole engine would melt. But luckily, it only lasts for a very small fraction of the running time. In the newest heat engine, the gas turbine, there is not this intermittent cooling. So the development of the gas turbine depended on finding the right metals. Metals which could rotate very fast without distortion while in continuous contact with gases at a temperature of 600 or 700 degrees centigrade. By 1940, new metallic alloys had been developed which could stand these continuous stresses at high temperatures. The development of these alloys helped to make the first gas turbines possible. Research will allow still higher gas temperatures in the future. This will mean more efficient gas turbines for industry and transport. Since men first succeeded in turning heat into useful work, engineers have been aiming at higher thermal efficiencies, which means saving in fuel and money. Today, civilization runs on heat engines. And they all depend on the simple fact that heat must flow from hot to cold.